Going on to 2.4, these are on what's called exact equations. So what we want to look at is the differentiable of a function in two variables. Kind of remind you of that first, what a differential looks like, and then what the form looks like. So this is what we have. So if z is equal to f of xy and has continuous first partials. So continuous first partials in a region R, so in R in the xy plane, and I could have written out xy plane, but I figured I'd show you some other set notation stuff you might see in the future. So it's the set xy such that x, y are in R. That's basically the xy plane. So xy plane. Then, so z has continuous first partials, then the differentiable can be written like this. So then its differential is dz equal to partial f respect to x dx plus partial f respect to y dy. And we'll call that equation 1. All right, so then I'm going to highlight this here. We'll come back to that function. Now, suppose f of xy equals a constant c. So it's kind of like a, it's going to be, I'll call this later, it's a family of functions. It's like the level curves of a three-dimensional figure, right? And if you hold f of xy constant, then you get like all the level curves. Okay, so suppose f of x is that, c is real. So that's a special case of this equation. Okay, so I won't write that out. So this is a special case of z equals f of x, y. So we're saying it's held to be constant. Okay, then 1, so that equation, so the equation above, we'll write that all out again. Then that equation implies that whole thing equals 0. So when you do the dz, you're going to get zeros. You're going to get 0. So you're really just rewriting this whole thing like here. I'll just copy it and paste it. Equals 0. Okay. Okay, so we'll call, so I forgot to say implies. That equation is equal to 0. So here's the concept. So given the family of functions f of x, y equal to c, we can generate a first order differential equation by computing the differential on both sides, by basically taking the derivative on both sides. So that's what I'm about to state here. So we can generate a first order differential equation by computing the differential on both sides. Now, it's easiest to show with an example. So, for example, if we have x squared minus 5xy plus y cubed equal to c, so it's not equal to another variable, right? It's not equal to z, it's equal to a constant. Then the equation above, then 2 gives the first order differential equation. So you just take those partials and you put it in that form. So that form would be, so take the partials with respect to x first, and then with respect to y. And so you'd get 2x minus 5y dx plus negative 5x plus 3y squared dy equal to 0. We're going to call that equation 3. So the form looks like this. The form is something we've seen before, kind of. So 4xy dx, as I said 4, m of xy. So we're going to call that m, and then the second one n of xy dy equal to 0. Okay. So that's where the term comes from. So this is, I'll say it like this. This is exactly, meaning exact, the form of a differential. So this is exactly the form of a differential. So that's what we're basically trying to look at, and then we're going to look at and see when we can use the technique to solve it. So this is the definition of an exact equation. So, the definition of what we call exact equation. Or exact differential form. So exact differential form. Okay, well, we pretty much have it. I'll just write it up. We're good. Okay, you can fast forward this if you want. So a differential, we have most of this already written down, so this is just redundant, but that's okay. So a differential expression, a little bit of nuance in the vocab and language really that I'm trying to get at here. So a differential expression, m of xy dx plus n xy dy is an exact differential in R, so in a region R in the xy plane, if it corresponds to So write it as to the differential of some function f(x,y) that's defined on the same region R. So if you can find the differential of f(x,y), it ends up being that form, then then that's called an exact equation. So a first order and I'll go ahead and start abbreviating finally. Differential equation of the form mxy dx plus nxy dy equal to 0 is an exact equation if the left-hand side is an exact differential. So kind of in some ways being redundant, but it's talking about the difference between the expression and the equation in the differential form. So read it through and just kind of get a feel for it. So a lot of, I think, extra wording there, but the key then is to figure out when that exact form. So we're going to not be given f of x, y. We're going to find f of x, y. We're going to be given this form, and we want to know when can you find f of x, y. Is it an exact equation? So that's where we're heading to next. So the next theorem are what we say are the necessary and sufficient conditions for that to be true. And I wanted to put this in here to show you some of the language we're going to use for necessary and sufficient. So I'm going to just copy this over from my notes that I have already. So we're going to copy this over. There we go. So we're going to copy this. And so go ahead and you don't have to copy that, but just read through that. And then one other thing I wanted to copy over was some of this language here I wrote down right here before we get to the rest of it. So my other notes, I put that ahead of it, but I wanted to put it here for our purposes. So when we talk about necessary and sufficient, this describes what that means. So we have, before I do the theorem, we'll talk about this a little bit. So we're talking about an implication, P implies Q, right here. And if you look at this type of statement, this is kind of an example you can use, and they just use greater than. So when you see the if and only if, and this stuff you may have already, probably already studied a lot of this at this point, but thought I'd throw it in here just to be a little more careful. So Q necessary for P, and then here's a sufficient. P is sufficient for Q. So those directions they talk about in the book a little bit. Anyway, I'll leave that there for you. Let's talk about the next theorem, and I only show one side of this, so that's kind of why I did that.